Purpose of this video is to apply the law of conservation of energy to analyze the motion of objects under the influence of springs. Let's take a look at an example of a block attached to a wall, I suppose, that slides across a frictionless table. A force of 30 newtons is used to compress this spring 20 centimeters, and then it's released from that position, and we're asked how fast will the block be moving when it reaches a displacement of 10 centimeters. Now, that's an energy problem, but if you look at this line right here where it says a force of 30 newtons over a distance 20 centimeters, that's a hint right there that you can get your constant value, because you know that the force divided by the distance traveled is going to be your value k. So in this case, k is going to be 30 newtons per 0.2 meters. So your k value is going to be, looks like 150 newtons per meter. So that's a piece of information that we're going to need later. Now they asked for how fast we're going to be moving when the displacement is 10 centimeters. So this box right here, which is attached to a spring, it's going to be displaced from equilibrium. It's already displaced 20 centimeters, but we want to know how fast it's going to be moving when it's only displaced 10 centimeters. So it's still not at equilibrium yet. So we've got the picture. We're going to apply the law of conservation of energy. That means the amount of energy you have initial is going to be equal to the amount of energy you have in the end. Well, what do we have initially? We've stretched the spring 20 centimeters, and we're at rest. We're waiting to be released. We call that elastic potential energy. Now, in the end, we're still not at equilibrium yet, so we still have some elastic potential energy stored up. So I'll say elastic potential final. Plus we're also moving, so we're going to have some kinetic energy final. Okay, so now we're going to apply our formulas. We know that elastic potential energy is quantified by 1/2 kx squared. So we will apply that formula to both. I'm calling time 0 and time 1 for initial and final. And the formula for kinetic energy is 1/2 mv squared. Okay, so we want to solve for how fast we're going. So that's this term right here. That means we should do some algebraic rearranging of the rest of our terms. So I'm going to subtract this 1/2 k x1 squared from both sides. And I get 1/2 k x naught squared minus x1 squared equals 1/2 m v final squared. Now the 1/2 term is on both sides, so we don't need that anymore if we multiply by the reciprocal. And we want to get v final by itself, so if we divide both sides by m, then we have an expression for v squared. So we want to take the square root of that, and in the end we're going to have the square root of k times x naught squared minus the other x squared, so the 20 centimeters and the 10 centimeters, all divided by the mass. Now at this point you just want to plug in your values and you've solved for velocity. And you should get a value of around 3.35 meters per second. And you plug in. Okay, now you try one. Attempt the following problem and then check your answer when you're ready. A 280-gram block of wood is firmly attached to a very light horizontal spring. So same image as above, this image. And the block can slide along a table where there's a coefficient of friction of 0.30 and a 22 Newton force compresses this spring 18 centimeters. If the spring is released from this position, how far beyond its equilibrium point will it stretch on its first swing? Okay, give that a try and check your work when you're ready.